University of Science and Technology under Hong Kong PhD Fellowship Scheme and BTech Assistant Professor at IIT Guwahati and part-time World Bank consultant for monitoring transport infrastructure project in Assam, India. His research focused on development and utilization of sustainable material, biochar fiber, including vegetation for geo-environmental applications. He has been awarded prestigious Telford Premium Prize for 2020 from British Civil Engineer Association for publication in Geotechnicators ICE UK. His research group has been also mentioned, referred to green infrastructure and water, and analysis of global research by Caparros Martinez et al. 2020 for the greatest number of publications and citations in Web of Science in research related to green infrastructure from 2010 to 2019. He is also currently guest editor for special issues related to Internet of Things, IoT, and artificial intelligence in geotechnical engineering in Journal of Rock Mechanics and Geotechnical Engineering. Besides, he was awarded Talented Youth Scientist Program Young Doctor Award from Ministry of Education, Guangdong, and International Scientist Exchange Program. Further, he currently presides over National Natural Science Foundation of China Youth Project on Vegetation for Soil Remediation. He has been invited to deliver lecture in various universities in UK, Japan, Germany, Macau, Taiwan, and Thailand. Not taking much time, I would like to invite our guest speaker, Dr. Ankit Gargsak, to start the session. Thank you.
Thank you, Dr. Skanda, for your kind introduction. I would also like to thank the administration of KIIT for organizing a very interesting faculty development program on a very important topic. And also, I would like to thank Head of Department of Civil Engineering and also Dr. Madhulisa for coordinating this particular FDP and making it a very successful program. And with this, I would like to start my lecture. I understood from Dr. Madhulisa that there are participants with mixed background. I mean, maybe some of you are in civil structural, maybe some of you are in geotechnical, and even in geotechnical, maybe you are not purely in geoenvironmental, maybe you are in more soil structure interaction. So this topic I will discuss in a more simplified way so that you can understand from different perspective, although your background is different. And also I will discuss a little bit about forensic part, which I think the numerical back analysis is very important for forensic analysis. I mean, it's not, this topic may not be directly related to it, but it's the numerical back analysis part, which is included, has direct relation with forensic analysis, because in forensic analysis and geotechnical, if we have to back analyze what has happened, I mean, in simple words, if I say, or what caused any kind of failure or any kind of instability or excessive deformation in soil. So we need to use both numerical modeling and also experimental part, which may include laboratory testing, elemental testing, and also maybe in situ determination of properties of soil. So I will continue with this lecture. Okay, so this topic is more about, as you can see, it's more about understanding how plants or vegetation influence soil suction. So I will also give idea about soil suction. Soil suction, in very simple terms, we can relate it, or we can understand in form of, you can say, tension that exists at the air-water interface inside soil. So it's a kind of force which helps to hold the soil particles together. Okay, so in this lecture, I will introduce you first what is soil root water atmospheric interaction and how this interaction is very important to be considered in geotechnical engineering, specifically if we are designing for bioengineered infrastructure, which has become very popular and very important in 21st century due to uh, threat, or you can say, or consequences of climate change, and also with the goal that we have to reduce carbon emissions by 2030 and 2050 as per UN. So we need to uh, go for more eco-friendly solutions. Okay. And then I will discuss a little bit about water flow in saturated and unsaturated soils. I think this may be useful for uh, audience and not maybe not specific in geotechnical background, but to give a little bit idea of how we modify this water flow in both the soils to consider root water uptake. And then I will consider a case study where we can study how density of soil can impact your soil suction. So from engineers point of view, we like to have more density, but from agriculture point of view, if we increase soil density or compaction, our plant growth may suffer. So we want to see whether increase in soil density will really be beneficial or not. Okay. So within this part, I will discuss about this numerical back analysis and little bit mention about how one should be very careful when we conduct this analysis, since and how we can obtain parameters which are not directly I mean, you can get it from literature. And then I will summarize my work. So in soil plant water atmospheric interaction, we are looking at how water flow in this entire system, including soil, then plant and atmosphere. So you can see vegetation through its transpiration. It can drive the water flow in the soils. So if we look at this part, uh, Dr. Madhulisa.
Yes.
So the annotation is not allowed, is it? Uh, Annotations means like to use the pen or the marker.
Think.
Okay, I can see here on the bottom. Yeah, it's okay.
Yeah.
Okay, so usually with this transpiration, what I was telling, this process is very important because we have all understood this process maybe in our high school or in biology class. So this transpiration is the loss of moisture through leaves, which happens in the atmosphere. And this transpiration, it creates a hydraulic gradient, which will help to move the water from, you can say, stem to the leaves, and then from root towards the stem, and from soil towards the roots. So it is this process which helps to drive or create a gradient, which drives the water from all the way from the soil to the leaves. And then from leaves, it gets lost to atmosphere. Okay. At the same time, you have evaporation happening from the soil, and you can have infiltration mainly during rainfall or during some manual intervention. And you also, and at the same time, we have solar energy, which is impacting the growth of plants. So this complex interaction has to be considered in our geotechnical engineering if we have to model green slope or bioengineered infrastructure, or if you have to improve the design of it. So at current stage, there is no such standard available that consider this complex infrastructure in our design of green slopes or engineering infrastructure. Okay. So we know in our typical soil profile, this zone, usually above the water table, you can say, except this capillary fringe zone, is mainly unsaturated zone. So unsaturated zone means like your degree of saturation is less than 95%, you can say. So usually we never have saturated soil. In real conditions, soil completely saturated is rare, very rare to exist. I mean, completely saturated means degree of saturation 100%. Even in laboratory, in the lab, it's very hard to make a very saturated specimen because we need to apply back pressure to remove any air or dissolved air in the soil. So that's why most of our soils in real life is unsaturated. Okay, and in unsaturated also, if you look at this point, this part where the root zone exists. So what we are looking here is want to see how we can model this interaction. Okay, so in people from agriculture, they have tried very simple root water uptake models to model how water will be taken by roots and will be close to atmosphere by transpiration. So in this zone, in root zone, how we model transpiration or root water uptake, something we are looking in this particular, I will discuss in this particular lecture. Okay, and also we will go through some basic terminology, which is very important. So I'm sure we have seen all this in our undergraduate studies, where soil is considered to be basically a three-phase material, which consists of air, water, and solid. But in unsaturated, there is one more phase, which actually uh, I'm sure some of you might be knowing already. So, so, so there is one more phase here. Okay, this side. So which is called air-water interface. So this phase is a very thin layer, or we can call it fourth phase of the soil. So usually in our textbooks, I mean in undergraduate, we have seen three phase, but in unsaturated, we also have a fourth phase, which is called air-water interface. So this air-water interface is actually the most smallest one, or very thin phase, but it's actually very powerful. Okay, in very simple words, I'm saying this is actually the phase which controls the strength of the soil. Okay, one of the major part. Okay, another part, of course, is solid. Solid also take up a lot of stress, but apart from solid, this is the most strongest phase, I would say, air-water interface. And this air-water interface is what we define as we define in terms of surface tension, and you can also call it soil suction. Okay, so there is this fourth phase in the soil, which is considered in unsaturated, okay, phase. And in a typical profile containing trees and soil and roots. So in the roots, you have, as I said, this is soil particle, this is water, okay, and you have roots, this is roots, and you have also air in it, okay. So your roots try to capture the water, or the water can flow through roots from the very minute pores of the soil, okay. And in that minute pores of the soil, the water is usually held in form of tension, this kind of surface tension. And also it may be bulk water. So this water is more or less bulk water, okay, like little bit free. But this water is held, okay, is held in surface tension. So in very simple analogy, I can say that when we take a shower, right, we wash ourselves with a towel, okay. So, and you have seen towel, right? So in towel, when you make your towel wet, or when it get wet, so there is two types of water in the towel. One is bulk water, okay. One is capillary water. And when you squeeze your towel, the water which comes out first, okay, just little bit squeeze it, your towel, and the water which comes out is more or less bulk water, because it was not held under tension, or the force was very less, and it comes out very fast. So that is bulk water. And when you keep on squeezing, you will see your towel is still wet, it's not getting dry. And that water which is held in the towel, okay, after squeezing, is, you can say, more or less, it's this capillary water, okay, the water which is held by air, this air water. That water which is after squeezing the towel, which is left, is more or less capillary water. And that's why it's very difficult to take it out. So you put it in the sun, you dry it out, and also in the sun also it takes time. So you can imagine the amount of force at which this water is held in the pores of the towel, okay. So you can imagine soil is also like a porous material, is like a towel which keeps two types of water in it mainly, okay. Most of the soils, I'm saying sandy soils, not clay. So it can have bulk water, which is very easy to take it out, and then it can have capillary water, which is very difficult to take it out because it is held by soil suction, okay. And same thing for plants. Now imagine that if plants have to take water from the soil, they have two types of water. One is bulk water, which is more free, and one is capillary water. Okay, because the roots of the plants are very fine. Okay, and more or less they get embedded in the soil, so they actually can easily also take up. Okay, to some extent they can easily take up the water which is present in the fine pores also. Okay, and but if you have too much bulk water, there is another problem which plants face, is that they call problems in metabolic processes, which can due to lack of oxygen. Okay, or that lack of oxygen from the air, so it can also hinders their function to absorb water. Okay, we will talk about later, but most importantly what I want to say is, uh, just from this slide, just remember there are two types of water, one is bulk and one is the water which is held at the air water interface. So there are two water. And another example of soil suction, as I said, is in the castle. If you go near the beach, I'm sure you cannot make this castle, sand castle, using very dry soil or even with very wet soil. Only with very optimum water content, or you can say when soil is all unsaturated, you can make it. And the reason is why it can stand 90 degrees like this is because of the tension which is held at air water interface. Okay, it holds the soil particles together and increases the strength. This is one example. Another example is this mosquitoes which can float on the surface of water is because in between their legs and the water there is this air water interface, and this gives them a lot of strength to float or to remain on the water. Okay, so this is an example of soil suction. A very classic example is sandcastle. Okay, so you can, if you put water on it, just imagine if you put a lot of water on it, it will collapse, right? Because as I said, this water which is required to make it 90 degree or to make it strong is not the bulk water. It's this capillary water. Okay, remember this capillary water is something which is very, very important in our unsaturated soil mechanics. Okay. And as I said, capillary water, you can imagine in form of capillary model. Okay, you can imagine this tube. This tube is like the pore of a soil, okay, or the void space, which can hold water in this capillary tube. The radius you can imagine is similar to the radius of soil pores. And the water in this tube is held under tension. Okay, so we can call it tension head, we can call it pressure head, we can also call it suction head. So there are different words are there. The meaning is same, the physical meaning is same. If you read books from agriculture, soil science, geotechnical engineering, I can tell you all of them, they tend to use different types of words for the same thing. Like in agriculture, in hydrology, they will use pressure head, or they sometimes even say matrix potential head. In soil, in agriculture, sometimes it goes towards this tension head also. Okay, and the units also change. Somebody represents in centimeters, somebody represents in kilopascal. In geotechnical engineering, we say suction. Okay, and we represent in form of kilopascal because we are engineers. Okay, but in agriculture and all represents in. I'm saying this because when you teach or when students comes to us with different words, because they read different books and they read from different articles from different journals, which may be from not only from engineering, from hydrology or soil science, they get confused sometimes. So the most important thing which I think we all should remember is that the physics remains same and the meaning is same. You can call it suction head, pressure head, tension head, uh, all these terms, the meaning is same. So as I said, this sandcastle could stand is because of soil suction. This is very simplified form, okay, for relating using this capillary model. I think you know this. The height of this water in this capillary tube, we can find it by using equation, which is called, we can say, capillary model 2 times tension into, there is another term cos alpha, we assume it to be 1 divided by radius. So this radius you can assume to be equal to pore radius, okay, of soil. And this has direct use in our unsaturated soil for estimating shear strength. So this, I think you are aware of the Mohr column envelope. The shear strength you can calculate using C and tan phi usually, and your net stress. But when you have soil suction, there is additional term which is added. Okay, so there are terms which have been defined by Professor Vanapalli in 1996 and Professor Fredland from 1995. I think they're more or less, they're from both Canada. Professor Vanapalli is, I think, an Indian, but he's in Canada. And I think they both were together in the same research group. So that's why you see very similar equations. So this equation also consider this term suction. So this term is also known as soil suction. Okay. And you can use this soil suction to estimate the strength. So you can see with an increase in suction, your shear strength will increase usually. Okay. And this term is not permanent. It depends totally on the soil suction which is present in soil. If your suction is zero when soil is wet completely, if I use simple terms, then your shear strength becomes zero. Okay. You can also estimate permeability of soil if you know soil suction using this term. So these are all modifications from saturated soils to unsaturated soil, and this is important because we are looking at problem where we need to understand water flow in this zone, which is unsaturated zone. Okay. So you can also measure metric suction in laboratory using several instruments, but in the field, we usually go for tangiometers. So this can measure reliably, you can say, from 0 to roughly 80. In manual, it will be written 90 kPa, 90 kilopascal, but even if you reach 70 or 80 kilopascal, you will see the readings are not reliable. Okay, so I usually 0 kPa, or you can say plus minus. Okay, so if we use this tensiometer, you can measure soil suction, but if the suctions are very high, especially in soil, clay soils, then or when your soil gets very dry, your suction can reach above 80 kPa. Then there are different set of instruments that can be used. And this is also still a research topic, I would say. Till now, up to date, we don't have one particular instrument that we can use in the field to measure soil suction right from 0 kPa to maybe around 1500 kPa, which is the wilting point of the soil. So we don't have this long range instrument yet, a reliable one. We have certain instruments which measure soil suction indirectly, or you can deduce it, but it's not very reliable. Okay, you need a lot of calibration. So this is also a research topic which is still in progress, I would say. So in terms of vegetation, if we think about stabilizing man-made slopes, so usually vegetation, I think this topic has been researched very well in literature. They have been considered in similar to, you can say, soil nailing in providing reinforcement. But at the same time, you can also consider hydrological effects, which is by root water uptake. So the same Mohr column equation can be extended by considering soil suction. Okay, and root water uptake by plant, what will happen? It will reduce soil moisture, right? Because plants are uptaking the water, and this will lead to increase in soil suction. Because roots, what they will do, they will take a lot of water, especially bulk water, and the water which is left out will be mostly, okay, this capillary water, which will help to increase suction. Okay. Applications, I think, in especially in many hill slopes, or these days in slope remediation, they are trying to use mixed methods where they are also using nailing or concrete and mixed with vegetation. And also universities, they are promoting use of vegetation in a more scientific way or more engineered way to stabilize slopes, also provide aesthetic value, and also for water filtration. Okay. So to understand water flow, we will first go through various models which have been developed. I think in undergraduate we have seen Richard's equations and Darcy's law. So the law governing the water flow through porous medium was discovered by Henry Darcy, a very famous French engineer. So I think this equation is well known to most of you. So if we consider a small soil element and assume it's a homogeneous and uniform element, and the water flow through this element can be calculated using this equation, uh, where Q is the unit flow rate, okay, K is the permeability or saturated conductivity, and this term is very, very important. I think this is somewhere where many of us get confused, is total head gradient. Okay, so this term is not only pressure head gradient, but it also includes gravitational head gradient. So remember, this term is total hydraulic head gradient. Okay? And total hydraulic when we calculate total hydraulic gradient, so this is pressure gravitational head. This is pressure head or suction head, which I was talking about. So we use both gravitational head and pressure head. Okay. So that term you can call it, it's always better you call it total head. Okay. So you will not get confused. So that water flow rate we can measure using this equation. Okay, and then there's a equation which can be used for steady or transient flow of water in saturated or unsaturated soil. This is a very general equation in 3 dimensions. So in most of the studies, we actually go for 2-dimensional. I would say even simpler studies are there for 1-dimensional. So this term we neglect always. We assume that the water flow in 2 directions are similar. So in steady flow rate, there is this on the right hand side, the storage will become 0. Okay, so there is no additional storage of water. In isotropic and homogeneous medium, your permeability, okay, in X direction, Y and Z direction are similar. In steady state isotropic permeability, in homogeneous medium, in steady state, this term also becomes 0. So you have this term. So remember, in these terms, there is no consideration of vegetation yet or root water uptake. Okay, and if we consider all flow in only vertical direction, then these 2 terms is also 0. Okay, so then you get a simple term like this. Okay, so now before we go into detail of how to implement, so we'll try to understand what is soil water characteristic of. So every material, well, it's not only soil, it can be any porous material, have a characteristic of. Okay, it's not only soil, even our towel. Okay, we use towel every day, we use our towel. So that towel is also have their own characteristic of. Okay, any porous material have its characteristic of. Okay, and it's a kind of material property, you can say, in very simple terms. Okay, and this on the left hand side, you see on this is a y-axis. Okay, this is volumetric water content, and this is soil suction. As I said, this is a force with which water is held within the pores of the soil. Now, if we want to understand it, let us take very 2 simple extreme cases. Okay, let us consider a very wet soil or a very wet towel, a very wet one. So in very wet towel, your water content will be very high, right? Right. So in that case, your most of the water will be bulk water, right? So and your capillary water will be, the amount of capillary water may be very negligible. Okay, and if your capillary water is very negligible, you can imagine or you can assume your suction is very negligible, right? Your suction is very less because your capillary water is very less when your towel or when your soil is very wet, right? So this state is more, you can say, very wet state of soil. Okay, and this side you can think or you can imagine is kind of very dry state. Suppose you're squeezing your towel and you're taking most of the water out. Okay, you again put in washing machine, you're again squeezing it, but it may, not the washing machine which can completely dry your clothes, but there are a lot of washing machine which can, rinse it, or you can take enough water from your clothes. So after that, you will see still there is some moisture left. Okay, so maybe there's a condition when you have a dry state, okay, of a soil. In that condition, you will not have bulk water. So the any moisture which is present in the soil will be mostly capillary water, and in that case, your suction, of course, will be very high. So more or less, it means we know that your suction will decrease or increase if your soil will become more and more dry. Your suction will increase. So if your moisture content decrease of soil, your suction increase. So it's an inverse relation. So it, and also there is a point beyond which, okay, if you decrease the water content, your suction will increase tremendously. Okay, so up to this point, you can say up to this point, any change in water content, okay, or any increase in suction is not causing any change in water content. Okay, it means at this point, the air we define it by air entry value. It means at this till this point, we assume that there is no air present in the soil, or there is hardly any air. So beyond this point, the air starts to enter the pores of the soil. So this is the first point from where the air enters the first pore of the soil. So it's considered in a very idealized way. Of course, in reality, the soil pores, even though, as I said, you make it saturated enough, they still have air in it. Okay, but we assume that majority of the air will start enter in the soil on an average at this point. Okay, and beyond this point, if you see, there is a sharp reduction in water content with a small increase in suction. So some soils can even go like this. Some soils can go like this. So for soils which have higher fine content or clay content, you can say clay or silt content. Okay, the soil will, if you have more clay content, okay, it will take more longer. It can have more longer time and more water retention. Okay, you can say at any given suction, the water retention will be higher in soils with clay as compared to with sand. Okay, so because your clay is more finer, so that's why when you go to market to buy a towel, I'm saying in very simple terms, if your towel is very fine, okay, it has very fine pores, it can retain a lot of water. Okay, so even if you want to dry yourself using a towel or to use it, your towel can have enough capacity to take the water. Okay, similarly, also have their own characteristic of, okay, even for napkins or tissue paper or towels, you can determine similar characteristic of if you want. Okay, and as I said, your clay usually have higher water retention as compared to sandy soils. Okay, so you can see the unit here. So this graph is taken from literature in agriculture. So they prefer to write in PF units or centimeter, their pressure head. But don't get confused. The meaning is same. You can even convert this into kPa, kilopascal. Okay. So this is a general equation for research equation, we call it, for water flow in unsaturated soil. We can modify it, as I said, using this equation. We modified it by adding a sink term here. So remember, this term represents a change in water, okay, storage. So in this term, if you add sink term, it means what you are subtracting the water, means this amount of water change with time represents the amount of water which has been taken by the plant. So if you subtract a sink term from it, this sink term represents the root water uptake, which have been, so we apply this sink term in a root zone, okay, in the soil. And this sink term represents the amount of water which has been taken away by roots from the soil. And this sink term has been defined in literature as a function of three parameters. The first is alpha, or you can say transpiration reduction function. It's a function which is dependent on soil suction. The second term is root distribution. Of course, we also need to see how roots are distributed in the soil. Sometimes in some plants, most of the roots are present near the surface as compared to deeper depths. Okay. Then the third one is transpiration rate, which is dependent on climate or atmospheric parameters. Okay. So the first term help us to understand how the sink term is dependent on the state of soil. If your soil is very dry, your plant may not be able to take enough water. Okay, they will take some water, but very less. So you need to regulate this term. Okay, so you need to have a very good function. That is okay. In very wet and very dry state, your plant will not be, your root water uptake will be very less. In very dry or very wet, but in optimum water content of soil, your root water uptake is good. So this term will help to take care of it. The second term will help to regulate this root water uptake according to the distribution. Okay, so sometimes in some cases in plants, if there are more roots present at particular depth of soil, or if there are less roots present, so accordingly they will tell us, okay, maybe near the surface the root water uptake is more, deeper if you go, the root water uptake is less. So this function should be, of course, the function of your depth z from the surface. And this term we need, as I said, to regulate root water uptake as per atmospheric parameters. Suppose if it's raining, your humidity becomes very high, right, at that time. So when your humidity is very high in the atmosphere and it's raining, your transpiration rate from the plant will be very less, because the atmosphere already have enough moisture, and the gradient from the leaf to the atmosphere will not be enough. Okay, or at the night, even at the night, we have done experiments to prove what kind of transpiration can exist. Okay, at night also we know there is hardly any photosynthesis and transpiration, and because of which we need to regulate this function as a function of atmospheric parameters. So you can imagine this is a very complex interaction. In the beginning I've shown, which have been simplified using these three terms. This term consider effect of soil or soil suction. This term consider effect of roots, and this term consider effect of atmospheric parameters. So these three terms. So it is still a simplified term, but considering many different parameters. Let us go into the first term, which is called transpiration reduction function. Okay, so this term I put it in a very simple form. It's a ratio between actual transpiration and maximum transpiration. So its term will vary from 0 to 1. So if your soil is very wet, it's a 0. If it is very dry, it is also 0. So this is a very idealized and simplified form of function, which has been proposed in literature in 1978, actually. And many researchers were using this function, even in geotechnical engineering in 2010, 2003, to estimate, you can say, soil moisture or soil suction under presence of vegetation. But we have modified this equation during my doctoral studies also. These equations we modify for our particular plants, which we use in Hong Kong. And you can see that in our case, this is the one which is proposed in 1978, very simple one. So this green one is from our study, this green and red. So we use grass, we also use a tree, a small tree. So if you see, in case of small tree, the transpiration rate goes down very fast, even at the suctions of 10 to 100 kPa. Okay, but in literature, the one they are using, it takes much longer time. Okay, so especially for grass, you can see it goes down very fast. And then there is also these trees, 3 trees with different leaf area. So they are more or less similar. You can see that the trees looks much stronger than grass, because the normal transpiration rate of tree is higher than grass most of the time. Okay, at very high suction. So it means in slope under dry season, when your suction increase, because in dry season, what will happen? Your suction will increase, and your transpiration rate or root water uptake will reduce. And for grass, it can be dangerous, because beyond this point, if your suction increase, your transpiration rate will reduce quite significantly, and it can be harmful. So that's why trees, they are more powerful, they are more strong to resist dry seasons as compared to grass. So if you want to plant grass on the slope, okay, in terms of slope engineering, we need to be very careful. We need to think about the climate first. Do they have very long dry seasons? If less, then we need to have some maintenance measures in terms of maybe irrigation. We can't have dry seasons where we have grass. Okay. This is a first term, TRF. As I said, it takes care of the effect of soil. Okay. Now, second term is the root distribution function. So you can see you have grass, which have very shallow roots. Then you have maize, then you have roots, and also root type will matter, whether fibrous roots, taproot, or what kind of roots. So you can imagine if you have roots like this, so most of your roots are present near the surface and less roots are present below the surface. So if I plot a root density distribution, okay, it's a distribution of root density across there. You can imagine your density is higher here, and then your density is reducing. So this is Z, and this is suppose root density. I can say RD. It will reduce with that. So it means your water up may be more likely to be higher near the surface as compared to very deep depth. So this will affect in modeling. This will help us to take care of the root distribution. The third one is atmospheric parameter. I'm not going into today because I think it's very easy to understand that atmospheric parameters will impact transpiration rate. And there are many models in literature which take care of that particular function. Yeah. So mostly we use Penman and Monte equations. And we also determine the root area distribution for smaller trees, very small trees, okay, in the lab. So we found that the function vary more or less in like parabola. Okay. So there are certain depth at which your density of roots are maximum. It's neither near the surface nor at very deep depth. Okay, so you will expect more water to be uptaken at this particular depth. Okay. So this was all about, I mean, I went into basics of how we consider in a research equation a sink term, okay, that can consider these three types of functions. And this function, give you more idea, this function actually has also been used before just in 2020. It has been used also by researchers from Chinese Academy of Sciences. They have used our model to predict, to develop their model for landslide prediction, and also they have done prediction. So this model has been used already in 2020 by other researchers, which we developed in 2015. Okay, so now I will discuss about the case study which we used these parameters and also modeling of root water uptake to understand how soil density affect transpiration induced suction. So this has been published in Journal of Plant Nutrition and Soil Science in 2015. Okay. So our hypothesis was like this. If I use this slide in a very simple way, we know the soil compaction, it will reduce pore size and can increase your water retention in general and induce suction. So this is our engineer's perspective. And also increase in compaction will increase strength of soil. Okay, so we engineers like it. But at the same time, we have to think from the plant's point of view, because if we are going for man-made slopes or bioengineered infrastructure, we need to consider long-term perspective of vegetation. This can hinder plant growth and also root water uptake. Yeah, this is more biological perspective. Then, as I said, since this will influence both of them, what is a coupled effect? Okay, what will happen? I mean, in one hand, it's increasing strength from soil perspective, but on the other hand, it is also influencing plant growth, which can reduce soil strength in return. Because, as I said, your soil strength, shear strength, is a function of C, phi, I mean cohesion, then friction, then also another term is suction, and plus root reinforcement. So if you hinder plant growth, your reinforcement strength coming from roots and also from soil suction may be reduced, we hypothesize. And this may further influence your strength, overall strength, rather than looking only from engineering perspective. So for this, we did, I mean, this is one very simple flowchart. I think it's very important for numerical procedure and also back analysis. One thing we should remember that numerical modeling is done not to predict something, okay? It's never done that we want to predict this and we want to understand, we want to create a new knowledge, okay? Numerical modeling usually will not give us very new knowledge because the numerical modeling is mostly based on governing equations and boundary conditions, which are already well known, okay, which are established, and also the initial conditions we and also the procedure we give manually, everything. So it's more like a car, which already have functions inbuilt, which already have given set of equations, okay, which will perform according to what we give. But it can be used for one very good thing is it can be used to verify something which we don't understand from field or laboratory, okay? So in forensic analysis also, when we go for, suppose some failure have taken place of slope and we want to check what might have caused this failure of slope, or we want to understand the mechanism of failure. So then what you can do is you can think about certain scenarios, okay? Like here, what I have pointed some scenarios. So you need to think about scenarios, and then correspondingly, you need to think about possible mode of failure which you expect might have happened. Okay, so this hypothesis or scenarios you can try to verify using numerical model. So it's not like you can use blindly any numerical model or numerical modeling to predict something and then say that, okay, the settlement is this, now the stability is this. No, this is not the right way. The right way is, as I said, in forensic analysis, what they do, they go back, they call it numerical back analysis. They go back to the site, get the soil parameters, get everything from the site, okay, your boundary conditions and all. And also most important is the in situ parameters, okay, not only laboratory parameters, but in the site, in the field. And then you need to think about certain mechanism or certain failure modes. And then from that perspective, you need to model it, okay? So observation is very important first. Second is measurements. So measurement of whatever input parameters you think and boundary conditions is very important. Then you need to explain, means you need to think about certain scenarios and hypothesis, what you expect. So as I said, in compaction, the soil influence root growth. And what I expect is maybe this influence on number 2 will be more dominating as compared to number 1. So I expect it may happen. And then I will use numerical modeling to verify it. How I will verify? I will give certain scenarios and then try to understand what happens in different scenarios. Okay, so this is the main purpose of numerical modeling. What we use when we say prediction, okay, those are called class A predictions. I have not written here. So class A predictions means you have no idea of what is the settlement going to be of this foundation, for example, or what is going to be the failure mode. Okay, you just use the input parameters, whatever you're given and whatever you get, and you have boundary conditions, and you just do modeling, okay, as a typical modeling procedure. So whatever calculations you get, those are called class A predictions. You don't know what is it right or wrong? You don't know because you just use parameters available and you predict it. Okay, in numerical back analysis, I mean, this is more like class C prediction, we say it. In numerical back analysis, we actually have to validate our model, okay, which is very important. And then you have to, after that, do the modeling procedure. And in that forensic analysis, it's very important again to consider uncertainty. Okay, I have not done it here in this lecture, but just for your reference, you need to consider uncertainties also in the properties of soil, whatever you're measuring, and also the governing equation in the numerical model. So all these things have to be considered. I would say, in other words, your methodology, research methodology should be very rigorous if you want to go for forensic analysis. And that's the whole idea behind it. Other things are more or less fundamentals that we need to follow, whether it's geotechnical engineering, whether it's structural engineering. Most importantly, I think, is the right methodology, research methodology that is needed. So as I said, we need to have different scenarios. So in our case, we took 3 scenarios. We think Maybe soil compaction only influence soil properties. So this is scenario one. So in scenario one, we have three different analyses. In scenario two, we assume the soil compaction only influence root characteristics. In scenario three, we assume their coupling, okay, which is more realistic, scenario three. So by comparing results from these three scenarios, we can find, first of all, we can find individual effect of compaction on soil and also on root water uptake, then individual impact of compaction on characteristics and root water uptake, and then individual simultaneous impact. Okay, so I have designed the three different cases. Okay, these two you can call it hypothetical scenarios. Okay, in real life it may not exist. Okay, because in real life scenario three exists. You can call it more like hypothetical scenario. This is just to verify or to understand what's the difference between individual and simultaneous conditions of compaction. Okay, and for there are two parameters, one is soil and root parameters. So for root parameters, to understand soil density effect, we inferred from literature. I will show you later. So for loose soil, the soil which is very loose, we assume, we idealize that roots will be more or less uniform because it's very easy for roots to grow in different directions in loose soil. But when your soil is very dense, you will see more roots are present near the surface of soil, and less roots will go at the deeper depths because there will be resistance. Okay, so you can assume in soil with higher compaction, your roots are more in the surface than in the at the subsurface. So your density of roots is more higher at the surface. So this is idealized case we inferred from this literature. Transpiration reduction function, we measure it, and rate, we analyze it. So this is the equation. I think you already saw it before. This is the measured functions. And this is idealization. Give you idea in loose soil, we assume that roots are more or less uniform in the cases, okay, up to certain depth. Of course, after that becomes zero. This is very idealized and simplified case. Okay, and with if your degree of compaction of soil is higher, you can assume your roots are more or less present near the surface, and then it reduces. So this may be a longer roots, then shorter roots, then shorter roots like this. So you can assume to be like, you can also call it, you can also use it parabolic or non-linear, it's up to you. Okay, but for simplicity, we just use linear decreasing. So this is how we infer from literature. And we also use WCCs of soil with different compaction. So this is at compaction, 82% degree of compaction. This is at 89%. So you can see when your compaction is higher, your initial water content is less, but when you go to unsaturated state, in your highly compacted soil have more water content because the pores are very fine. Okay, so you can see the permeability change also. So when your compaction is higher, of course your saturated permeability will be less, right? Saturated permeability in compacted soil will be less than, or in loose soil, your saturated permeability is more than dense soil. We know it. But in unsaturated case, it's opposite. In unsaturated, what happens is, because of the presence of air, your unsaturated permeability may become different or opposite in loose and dense soil. Okay. And for the back analysis, we did experimental testing in control room in Hong Kong. And we did we designed these experiments to measure plant transpiration rate, okay, which we calculate using water balance. And also we measured soil suction. This sensor I was talking about, this sensor is for light radiation. This sensor, we talk about suction measurement for 0 to 80 kPa. And this sensor, we call it heat dissipation sensor. So it measures, or you can say estimate suction, not directly measure. It gives you idea of suction using thermal change in, you can say, temperature in the soil. So it will release some heat. Your temperature change in the soil will depend on heat conductivity, thermal conductivity, which in turn depends on moisture content. So it's an indirect measurement of soil suction if you want to go measure suction beyond 100 kPa. Okay, so within 80 kPa, we use tensiometer, which are more reliable, I would say. And we validated our transpiration rate based on the suctions that we measure in the lab. So this was very important. Same thing, maybe in forensic analysis when you go, uh, numerical validation of your validation of your model is very important. Okay, that's the only way of validation. And you can also validate either field measurements, you can also validate using laboratory measurements. Suggestion will be to go for laboratory because it is more simple and easy to control. In field measurements validation, you can do, but you never know whether it is by luck or is it really true validation. Okay, in field, what happens sometimes there are a lot of factors affecting, and maybe one factor can subtract the influence of another factor. So your validation of measurements in field is more difficult. And even if it becomes true, you don't know is it real true or is it apparent. Okay, so I suggest for all the modeling, it's better to do with the lab. So it's a typical procedure for numerical modeling. Here they have not written, but validation is very, very important of model. Okay. So then for after validation, we consider the domain, again, a ground with the axis, we consider axisymmetric analysis with the tree planted, and we assume a root zone of root lateral length LR and VR. Okay. And this boundary we specified a transpiration rate boundary. We assume now the evaporation effects are negligible. And we use steady state first initial condition to determine, and then we consider drying period for at least 10 days. Okay. So our results consider individual and couple effects. So this is a typical pore water pressure profile or suction profile, you can say negative pore water pressure. So this is the initial condition, this one. This one is a condition you can see with uniform root distribution. This is a more or less individual impact. Okay. This is, you can say, hydraulic conductivity only. This impact consider both SWCC hydraulic conductivity, okay, at two different densities, 80 and 90%. Okay, so if you can see here, this curve, okay, the influence zone is much higher, longer. Okay. And for this case, these two cases. So in this two cases, the difference is in hydraulic conductivity SWCC. So if you consider the impact on SWCC, you can see that your suction gets reduced quite significantly with the increase in compaction. So here you can see your hydraulic conductivity is corresponding to higher compaction. So if you, when your hydraulic conductivity reduce, your water flow will not happen much, okay, and this suction reduce quite significantly. And in 90% with 90% close to compaction, here if you see these two cases, this one and this one. Okay, so near the surface there will be a difference because of hydraulic conductivity, but if you go at the deeper depths, okay, this case has more less suction, okay, as compared to this case, 80%. So it means your, if you have a vegetation, okay, if you're talking about uh, geo infrastructure or geotechnical structure which you want to establish beyond this depth, okay, the difference is not higher, so there's not much influence. But within this zone, for shallow slope failures, these two cases looks much better because this case and this case looks much promising because it gives much higher suctions in the shallow range. Okay, but this case is not promising. Suction at surface increase by 27%. The moment you consider density effect on hydraulic properties, your slope of SWCC less steep, okay, higher suction because of given root water uptake, and slope of SW, because here if you see it in these two cases, the moment you increase compaction, okay, your slope becomes very flat. So if you reduce water from, suppose from this to this, the increase in suction is much higher for higher compaction. Okay, that is why here you see much higher increase in suction for this case, last case. because you need to also consider the slope of SWCC. Here you consider these two cases represents your effect of compaction on hydraulic properties only. Here you have to consider root depth. So once you consider effect of compaction on root characteristics, you see your variation lies here. And if you consider only soil case, like scenario 1, this is scenario 1, okay, and this is scenario 3. Remember this couple effect. So you see your suction reduced quite significantly. So it means in long term, your higher compaction may not be very beneficial for increasing soil strength because you are limiting plant growth, you are limiting root water uptake, and you're limiting the transpiration or plant-induced soil suction. So that may be very important for long term, especially for shallow slope failures. And that's where if you have to go for man-made slope, engineer slopes, maybe we need to consider an optimum density, or maybe we need to consider specific vegetation which can tolerate higher compaction resistance. So to summarize, this change is something we were having some hypothesis, and the main reason is reduction in the root depth, in compaction and transpiration rate, which can cause counters the increase in permeability. So this effect, the couple effect, shows that it's not really advising, because if you consider compaction effect on hydraulic property, it helps us also in compaction and also in increasing suction. But if we consider the moment we consider plant effect due to compaction, our suction induced becomes lower. Okay, and this is because of the decrease in root depth and also root distribution. As I said, in high compaction, your roots are not uniform like this. Your density reduced with depth. So you need to consider this into account. So in summary, your root water uptake induced suction can be modeled using Richard's equation. So even for forensic analysis, if you want to go for numerical back analysis, we need to measure very soil specific or region specific plant parameters. Even if we inferred from literature, we need to justify it properly. Contrasting trend of suction was observed in, as I said, with and without considering influence in root characteristics. Your suction increased quite significantly if you don't consider effect of compaction on plant growth. But if you consider effect of compaction on plant growth, then you need to be worried, because as I said, your suction will reduce quite significantly here, or your strength of soil if you consider coupled effect. Okay, so with this, I'd like to end my PowerPoint and ready for discussions here. Okay, yeah, thank you.
So thank you so much, Dr. Ankit, and thank you for your wonderful lecture and valuable. It was really very interesting. And so now the participants, you can ask your questions if you have any. So any questions from any other participants? Any questions from the participants? So I think all the topics were like you discussed very clearly, and they also understood. I think they don't have any queries. Okay, sir. So it is an honor for me that you are the part of this FDP as an expert speaker, and really thank you so much for accepting the invitation. Thanks a lot.
Thank you, doctor. Yeah.
So with this, sir, you come to the conclusion of this session 40. I thank you all for your valuable presence and for your patience of listening. And now I request you all to kindly switch on your camera for one group photo. All of you, please switch on your video. All of you are requested, if you can. Okay, thank you so much, sir.
Thank you. Yeah.
So participant, again we
And the
will.
days are very tight. Exhausting 5 days. I think most of us are exhausted. So that you can give us a feedback because the 5 days, I think first time we are trying, but almost all of us are exhausted.
Sorry,
No,
sir.
This number to be
no, it's not being exhausted actually. I would like to sorry. It's like the topic itself is new for most of, maybe for me it is there, and maybe most of the for most of us also is there. So that is maybe not immediate questions, but before Kit sir leaves, I would like to appreciate him for the great session, and also if
Goyal ji ka bhi,
get back
the
to you,
morning
sir.
session
Thank you,
was
Garg
also
sir,
today. Goyal ji ka bhi, that was a
Professor,
very nice presentation.
because the
Our late,
presentation was
yeah.
really good, but not as the topic being new for maybe me and most of the us. So that is why no immediate questions, sir.
No problem, no problem. I mean, you can, email also later.
Yes, sir.
Other to routine, mostly routine, but Goyal ji ka, it was very innovative. Climate change.
Yes, sir. Email ID is with me. So if you need, then I can share with you. So later, if you will listen, then you can ask any type of your doubts. Okay, sir.
I do agree with Professor Dinesh Chauhanji that this is totally a very great and fantastic, different, unexplored area that we have been exposed to that, and that is the reason why, as rightly said. But this is very new and innovative and something different, giving a different direction for all of us to start with a new research area too. So it's really a good session. I appreciate and congratulate the organizers and the speaker for the same. Thank you.
Thank you. Thank you,
Professor.
so much. So is there anything like any questions, like any suggestion, yeah, from the participants? So we have our next session at 3 p.m. That is validatory session. So all are requested to join to the platform by using the same user ID and password, same link. Okay. Okay, sir. So with your permission, shall we end this session, sir? Dr. Ankit Garg.